In this highlight video, we are going to start talking about reactions of alkenes. Our first reaction will involve the hydrohalogenation of alkenes. Hydro just means H, halogenation, X, where X is either going to be bromine or chlorine. After you've watched this video, you should be able to sketch the products of the addition of hydrogen halides to alkenes and be able to write reasonable mechanisms for the addition of hydrogen halides to alkenes, including explaining observed regio and stereoselectivity. Here's an overview of the upcoming reactions. All of these reactions can be categorized as electrophilic addition reactions. That's because the alkene, like cyclohexene here, is going to act as a nucleophile, and it's going to react with electrophiles. If we look down this list, notice that in each case, in the product, the pi bond is gone and two new bonds are being formed. So the first reaction we'll do, this hydrohalogenation, involves the addition of HX. We see a new H attached to one carbon and X attached to the other carbon. We can also do such reactions where we use water. So we have an H attached to one side and an OH to the other side. This reaction is called a hydration because we're hydrating, we're adding water. We're going to look at two types of hydration reactions. One shown here. The other is shown down here. So don't get hung up on the different conditions yet. We'll go through those in detail. The last two both involve the reaction of the alkene with halogens, X2. And they differ only in a second step. So these two we're going to talk about together, and they have to do with hydrogenation. All right, so the first reaction we're going to talk about is the addition of HX, the hydrohalogenation. As we showed previously, what's going to happen, let's draw in all of these atoms first, is that the H will add to one of the carbons of the double bond, the bromine will add to the other carbon, and the pi bond will be gone. So there's our original H. Here's our new H. Here's our original H. Here's our bromine. This reaction takes place in two steps. The first step is a simple acid-base step. The pi bond acting as the base, reacting with the H of the acid. So this is just acid-base like we've seen before. In this process, we could protonate either of these carbons, but I'm just choosing the one on the left. We protonate that position. The pi bond was removed from the other carbon, so that leaves it short of electrons with a plus charge. So this intermediate is called a carbocation. All right, in the second step, the bromide that was liberated in the first step is drawn to the plus of the carbocation. So we could just call this step a Lewis base, Lewis acid step. And the other one, let's just say this is a base with an acid. We could use Bronsted-Lowry acid-base theory here, because we're transferring a proton, or we could call it a Lewis base, Lewis acid, the pi bond being the Lewis base, it's the electron pair donor, and the acid being the electron pair acceptor would be the Lewis acid. All right, so because we have two steps, if we look at the reaction energy diagram, we know we're going to have our reactant somewhere here, and our product, because it has all sigma bonds, is going to be somewhat lower in energy than the reactant. Remember that pi bonds are not as strong as sigma bonds. We have an intermediate, which is going to be the carbocation. It's going to be somewhere higher in energy. So we're going to have a transition state between our reactant and our intermediate, second transition state going to our product. So this is our alkene, this is our carbocation, and this is our product. We have seen carbocations before, so how else do we know how to make this carbocation? Well, it could be formed through an SN1 type of mechanism. Let's say if we have an iodide, the iodide could come off to form that carbocation. What else? All right, we might also form that from a secondary alcohol, right? If we react the secondary alcohol with HBr, right, we know that it would protonate the alcohol to form a water molecule that could leave to form the carbocation. So once we form the carbocation, it can do all the things that we've seen before. It doesn't matter whether it comes from the alkene, from the alcohol, or the alkyl halide. If our alkene is unsymmetrical, meaning that it has different groups bonded to each end, we have the possibility of forming different products, okay, of forming isomers. For example, we could add the H to this position here, add the chlorine over here. Alternatively, we could add the new H over here and the chlorine here, right? Is there any reason why those would be formed in equal amounts? Well, not really. Let's see if we can figure out which one of them would be formed as the major product. So let's build our reaction energy diagram. So we have a single reactant, alkene reactant. Okay, so we're going to do this like we did last time. Here's our reactant. And we know that this reaction is going to proceed through two different carbocations. We can either protonate on the 2 position, which would be here to form this carbocation, and this would lead to the first product that I drew. Alternatively, if the end carbon was protonated, it would form this carbocation, which could then generate the second product. So let's look at these 2 carbocations. Which one would be more stable? Well, the first one is a primary carbocation. The second one is tertiary. So what do you remember about stabilities of carbocations? So the more substituted a carbocation is, the more stable it becomes, because the alkyl groups attached to the carbocation are able to donate some electron density to help stabilize it. So this tertiary carbocation would be more stable. Right? The primary would actually be quite less stable. Okay, so let's draw these onto our reaction energy diagram then. We would have some point here, which could be our tertiary carbocation. Like this. And somewhere up above it, we would have our primary carbocation. Like this. And then somewhere over here we'd have our products. We can't really tell. It's not obvious which of those products would be more or less stable. Okay, so this would just be our two different products. We have one with the chlorine here. Oops. And one with the chlorine here. So let's concentrate on the first part. All right, we talked about, or mentioned, the textbook talked about more than I did, what was called the Hammond postulate. Okay, and that's what we need to be able to talk about this situation here. So we know that each of these reaction pathways is going to go over a transition state. All right, and what the Hammond postulate says is that for an endothermic reaction, the transition state is going to look like the product, or like our intermediate in this case. In the Hammond postulate, the transition state always looks most like the reactant or product, whichever it's closer to in energy. But because these are endothermic, the transition state will look like the product. So for an endothermic reaction, the transition state will look like the product. And what that means is if greater substitution of this tertiary carbocation, that same substitution is also going to be more stable for the transition state. So the transition state leading to the tertiary carbocation is going to be more stable than the transition state leading to the primary carbocation. So that means that this one will also be formed faster and will be our major product. So this one is going to be the major product. So this is going to go down here. This is going to go down like this. All right? So notice that the H has gone on this end. All right? So we can summarize all of this in what's called Markovnikov's rule. It states that in the addition of HX to an unsymmetrical alkene, the H will go to the less substituted carbon. All right, so notice this position has two H's on it. whereas the other one has 2 carbons attached. So less substituted means that there's less carbons. There's more H's. So less substituted carbon means more H's. So why does this rule work? The reason is because by protonating on the less substituted position, the position with more H's, we always will generate the more stable, more highly substituted carbocation. Let's apply Markovnikov's rule. So here we have a methyl cyclohexene, and we're adding to it HBr. So the H is going to go to the side with more H's. This side has 1 H, the other side has no H's. So our product will have 2 H's at this point. The methyl group and the bromine will go to the position where the most stable carbocation can reside. All right, so this would be our major product. All right, what about the next one? All right, we have 2 H's here and 1 H here. So if the H goes to the position with more H's, it would go out here on the end. We'd then have a methyl group with 3 H's, and our chlorine should go here, right? Well, not exactly. That's not going to be our major product. In this case, this is going to be our major product. So how do we get there? All right, so what needs to happen? So let's work forwards from here. All right, protonation of the double bond, just like we knew that it would. Forms a secondary carbocation. The other thing that we can know is that the chlorine is going to end up at a position where there was a carbocation, here. So how do we get from here to here? All right. Can we just jump the carbocation over? No, we can't do that. What we can do, however, is because we have this more highly substituted center here, we can do a, what is this called? A 1,2 hydride shift. So it goes from a secondary carbocation to a more stable tertiary carbocation. All right, this is the same kind of rearrangement we saw during dehydration reactions. And so this is something that you have to watch out for. Remember that whenever we form a carbocation, it can possibly rearrange if it can generate a more stable carbocation. We've seen that hydrohalogenation reactions can be regioselective because the H goes to the less substituted side, the halogen goes to the more substituted side, as described by Markovnikov's rule. So can hydrohalogenation reactions be stereoselective? So let's take a look. All right, so in this reaction, we would first protonate. The H would go out to the end, right, leaving us with a tertiary carbocation. All right, now the bromide, because we know that this carbocation is planar, the bromide could come either in from the top or it could come in from the bottom. All right, let's look at the two possible products then. All right, if it comes in from the top, it will be a wedge like this, and the methyl group will be going back. If it comes in from the bottom, it will have a dashed line going to the bromine, because it's down below, pushing the methyl group up, like this. So what's the relationship between these two molecules? These are the same, right? We just flip one of those over and it would superimpose right on the other one. So this first reaction would be regioselective because it's following Markovnikov's rule, but it is not stereoselective. All right, we don't generate any stereoisomers. Let's look at the next one. All right, so let's go down here. We're going to do a little mechanism. So let's protonate. We could protonate on either the top carbon or the bottom one. I'm going to protonate on the top one, and I'm going to arbitrarily say at this point that that new H protonated on the bottom to form this carbocation. It could also protonate on the top, and it's going to give us some enantiomers, all right, some stereoisomers. Let's just look at this to make this more simple. All right, so now the bromide, again, could come in from the top or the bottom. Let's draw our products. Okay, this center stays the same. It's got protonated on the bottom. We're going to bring the bromine from the top, and this methyl group will be on the bottom. All right, so notice that the H here and the bromine here are opposite of one another. So we call this anti. So it was an anti-addition. Now, if the bromine or the bromide comes in from the bottom, then bromine will be here. The methyl group is on top. So now the H and the bromine are on the same side. This is called a syn addition. Okay, so what is the relationship between these two? All right, so let's compare. At one position, at this position, the stereogenic center is the same. But notice this one, it's reversed. So if we have one the same, one reversed, what does that mean? The relationship is here. These are diastereomers. Okay, diastereomers are different in energy, and so the pathways leading to those will be different. All right, the energies in those pathways. So we would very well get an unequal mixture. And that means that we are getting more of one stereoisomer over the other, and so this reaction would be stereoselective. Is this reaction regioselective? No, because our starting material was symmetrical. The H could have gone to either end. We would have gotten the same constitutional isomer.